Start here.
Welcome everyone to the Colchin seminar in differential algebra. Today we have Joël Ouaknine speaking, and it's our pleasure to introduce him. Please go ahead.
Okay, thanks very much for having me. I'm just sharing my screen, just making sure. Can everyone see the slides? Yeah, good. Okay, so feel free to interrupt at any point. So this is joint work. This is about talk about holonomic techniques. If you've never heard of holonomic techniques, then of course fear not. There will be an introduction, and of course there's probably a number of areas in which people in the audience will know more than I do. So I apologize for if I make mistakes or if I belabor some things that are very obvious. I should also say this is joint work with a lot of people whom you see on the slide there. So let me start by quoting Don Knuth, who says science is, he's talking about art versus science, and he says, well, science is what we understand well enough to explain to a computer, and art is everything else we do. And so, and now just before I jump I go further ahead, let me just put a little bit of a propaganda slide here, which I've shamelessly, I should say, stolen from from a talk of Cyril Banderier, where you look at all these topics, right? I mean, you don't even have to read all of them. You just sort of just flashing these things. What do all these things have in common? And the answer is, perhaps somewhat surprisingly, is holonomic techniques. So let me just start with some examples. So suppose that you're trying to prove an identity, such as this, this identity you have on your screen there, this sum of binomial coefficient squared is equal to 2n choose n. Well, on the right-hand side, you have the number of ways you can choose n letters amongst 2n letters. And of course, there are 2n choose n ways to do that. On the left-hand side, you could say, well, I could choose k letters amongst the a's and then n minus k letters amongst the b's. And then, of course, I would have to sum over all possible values of k, and then I've counted the same thing. So then I conclude that this summation here, and then n choose n minus k, of course, is n choose k, so I've got the summation square is equal to 2n choose n. And I think Knuth would call this art. I mean, it's a cute little proof. It's a nice proof, but it's not at all in any way clear that it can be made systematic. If I were to change the square into a cube, then it's not at all clear. I would know how to prove the equivalent identity. Let's have a look at how the holonomic technique approach to proving such an identity. So here the idea is this. I'm going to label the sequence. So you have a sequence of numbers on the left-hand side because you have a number for every n, and likewise for the right-hand side. I'm going to label the sequence of numbers on the left-hand side un and vn for the sequence of numbers on the right-hand side. And a high-level strategy is to find a recurrence relation for the uns, find a recurrence relation for the vn's, and then from that obtain a recurrence relation for the difference un minus vn, and then finally verify that un minus vn is identically 0 by checking the initial values. Okay, so that's the high level. So let's see how this works in practice. So let's start with the right-hand side. So 2n choose n is 2n factorial, blah, blah, blah. So that's vn. vn plus 1 is 2n plus 2 choose n plus 1. And then I develop a little algebra, and I conclude that I have the following recurrence, which is n plus 1 squared times vn plus 1 is this polynomial times vn. Okay, so this is, I mean, you can check, of course. Then we can try to do the same for the left-hand side. The only problem is relating un plus 1 with un is not so easy. But nevertheless, the sum of the binomial coefficients squared is so-called sister-Celine summable. If you've never come across this, even this might sound funny to you. I'll come back to this a bit later. But the point is you can actually use something called Zeilberger's algorithm to conclude, to derive a recurrence relation between the un. So it turns out this recurrence relation is n plus 1 times un plus 1 is 4n plus 2 times un. And of course, you have to give the initial condition, which you just, by inspection, is u0 equals 1. And then finally, what do we have? Well, we've got the recurrence for the uns, the recurrence for the vn's. So un and vn, they both satisfied what are known as a holonomic recurrence relation of order 1. So it's holonomic because it involves polynomial coefficients. So you see these terms are polynomial. And it's order 1 because every term depends only on one previous term. Okay, so it's order 1. If it were like Fibonacci, it would be order 2. Therefore, now just by linear algebra, un minus vn will satisfy a holonomic recurrence relation of order 2. And therefore, you need only verify that u0 minus v0 and u1 minus v1 is 0. You don't even need to know, by the way, what the recurrence relation of order 2 is. You only have to check that the first two terms are 0, because then automatically, because you know it's order 2, you know that every term will then henceforth therefore be 0. And you'll conclude, therefore, that un minus vn is identically 0, or in other words, that un is equal to vn for all n. Okay, does that make sense? By the way, if there are any questions at some point, I assume the protocol is to leave something in the chat, and perhaps one of the hosts can just alert me, and happy to react in real time. Now let's have a look at a slightly more complicated example. So about 50 years ago, Roger Appéry produced this was described as sensational proof of the irrationality of zeta of 3. And the critical ingredient were these Appéry numbers, which are defined by this kind of combinatorial expression. And it turns out they obey the following holonomic recurrence, which you have on your screen. It doesn't matter exactly what it is, but you can see it's a holonomic recurrence. When Appéry was asked about where did this come from, he said, oh, these recurrences, they grow in my garden. He somehow said cryptically. He didn't prove it. It was kind of completely clear this recurrence was correct, because you can evaluate the first 5,000 terms, and you see that it's always equal to 0. So it has to be true, and it has to be provable, but he did not show how to do it. And van der Poorten teamed up with Henri Cohen, who was another famous number theorist, and they tried to actually prove it. And van der Poorten writes, neither Cohen nor I had been able to prove the above in the intervening 2 months between the time that Appéry presented his proof and the time that he was going to present it at the International Congress of Mathematicians. After days of fruitless effort, the specific problem was mentioned to Don Zagier, and with irritating speed, he showed that indeed the sequence satisfies the recurrence. This more or less broke the dam, and the rest of the proof was quickly conquered. But poor van der Poorten, he was a couple decades too early, because nowadays you can use Zalberger's algorithm that I alluded to before, not only to prove such recurrence, but actually to derive it from scratch. You don't even have to know what the recurrence is. And here's a picture of Doron Zalberger with a fitting t-shirt. And you can use, for instance, in Maple, the SumTools command, where you say sum recursion, and then you put the expression for the Appéry number, and automatically, within a fraction of a second, Maple will spit out the recurrence that the Appéry number satisfies. So you have not only, and it's provably correct, of course. Let's have a look at another example, a continuous example this time, because holonomic techniques sort of have this nice property, they mix the discrete and the continuous. So let me look at a continuous example. So suppose you want to prove that sine 2x is equal to 2 sine x cos x. And what do I mean by prove this? I have to say, what am I assuming? I'm going to assume the differential equations that sine and cos satisfy. So sine x, of course, sine x and cos x satisfies the same differential equation. It's just that the initial values are different. And so if I call the left-hand side, it's the same high-level strategy. I've got f of x on the left-hand side, g of x on the right-hand side. Of course, x is now a real, ranges over the reals. And by the box, I can immediately derive that 4f of x plus f double prime of x is 0. And therefore, in other words, f of x satisfies a second-order ODE. And g of x is a product of two functions, each of which satisfies a second-order ODE. So g of x by linear algebra will have order 4. So we'll satisfy this order 4 ODE. And therefore, the difference between f of x and g of x will satisfy an ODE of order at most 6. And again, I don't even have to, I can calculate it, of course, mechanically, but I don't even have to. I just need to check that the initial conditions are all 0. So h of 0, h prime of 0, dot, 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 up to the fifth derivative of h at 0 is 0. And once I have this, I automatically know that h is identically 0. In other words, that f of x is identically equal to g of x, and I've proven the identity I was going for. Okay, so again, if there are questions, just please free to ask. So let me define these things a little bit more formally. So a sequence of real numbers is so-called holonomic, or p finite, or p recursive, if it satisfies a linear recurrence relation with polynomial coefficients. So let me just be precise about this. So you have a series, a number of a bunch of univariate polynomials with rational coefficients, such that the sequence of numbers un satisfies that the n plus kth term of sequence times pk of n is a linear combination of the previous n terms in the sequence where the coefficients are the polynomials, each of the polynomials evaluated at n. Okay, so that's the holonomic recurrence relation. And so we've seen examples, the a priori numbers, and so on. There are plenty of examples. So n factorial is holonomic, the Fibonacci, any linear recurrent sequence with constant coefficients, of course, holonomic. So Fibonacci numbers in particular, harmonic numbers, Perrin numbers, etc. And also the Taylor coefficients of many, many functions. This is not a coincidence. So for instance, sine x is given by this Taylor series, and the coefficients have the following form. So 0, 1, 0, minus 1 over 3 factorial, 0, 1 over 5 factorial. And the recurrence is as follows, where you have to specify the first two values, 0 and 1. And so the Taylor coefficients of many trigonometric functions are themselves holonomic sequences. Manuel Cowers, a few years ago, claimed that approximately 25% of the sequences in the OEIS are actually holonomic. I don't know whether that has changed. I suspect not. Now, here are some non-examples. I won't dwell on why these are non-examples. It's all easy to prove for various reasons that these are non-examples. So not everything is holonomic, of course. And the good thing about holonomic sequences is that they have very nice closure properties. So for instance, if UN and Vn are holonomic sequences, then you can take their pointwise sum, pointwise product. You can shift the sequence. You can take the sequence of partial sums. You can take the Cauchy product of the two sequences. And all of these things are again, holonomic sequences, which makes it a great class for computer algebra, meaning for computer-assisted manipulation. These operations are all effective. So given the data that tells you that UN and Vn are holonomic sequences, you can automatically, mechanically produce the data that tells you the resulting sequence is itself holonomic. To define a holonomic sequence, you only need to provide the recurrence relation together with finitely many initial values. Okay, so it's, of course, the holonomic sequence is an infinite object, but you can define it using only a finite amount of data. And now the kind of one of the main theorems is that which is not the deep theorem, but I think it's important to realize this, that for two holonomic sequences, UN and Vn, with initial values in some field where you can do effective comparisons, such as here I'm writing the algebraic numbers, the equality problem, whether UN is identically the same as Vn, so UN is always equal to Vn, this is a decidable problem. There's an algorithm that can actually do this, provided the initial values belong to something where you can make comparisons. So the slogan is equality or identity is decidable for holonomic sequences. Okay? For holonomic functions, I need it's a little bit more technicality. So first of all, they may not be defined over the whole of R. So let's consider a function from some interval I into the real. So a function from the reals to reals, but it may only be defined in some interval I, is so-called holonomic or definite if it satisfies a linear differential, a linear ODE with polynomial coefficients. So very similar to before. So there exist univariate polynomials with rational coefficients such that P0 of x times f of x plus P1 of x times f prime of x plus dot 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 is equal to 0. So that's an order k linear differential equation with polynomial coefficients. And examples are many trigonometric functions, all algebraic functions, e to the x, log x, and so on. And many functions are holonomic. So again, according to Cowers, approximately 60% of the functions in Abramovitz and Stegun's handbook are themselves holonomic functions. They have nice closure properties, as you might expect. So if f and g are holonomic functions, then you can add them, multiply them, integrate them, differentiate them, write compose with an algebraic function, and all of the resulting objects are themselves, again, holonomic functions, and everything is effective. So the corresponding equality theorem, again, requires a tiny bit more. So let's assume, without loss of generality, let's assume that 0 belongs to the interval I, is in the domain of our function. How do you define a holonomic function? Well, you need to provide the differential equation together with finitely many initial values, f0, f prime, evaluated as 0. So f of 0, or evaluated at any point in the interval I. F of 0, f prime of 0, f double prime of 0, provided there is a little bit of proviso, technical proviso, 0 is not a root of the polynomial coefficient of the highest order term of the differential equation. Let's ignore this. This is very benign. And now the theorem says that for two holonomic functions f and g with initial values, algebraic numbers, so all of this data is algebra, all of the data here is algebraic numbers, the equality problem is decidable. So this equality between functions, so identity of functions, if you will. So again, for holonomic functions, as for holonomic sequences, equality is decidable. Okay. And we come to what I want to call the fundamental theorem of holonomy theory. I don't know that anybody else is calling it this. I think, it should be called that. And it says following. So let UN be a holonomic sequence, and now let us consider the generating function of the UN. So I formed this function f of x, now a function from the reals to the reals, which is the sum of UN x to the n. That as a function is holonomic. Okay, and conversely, the sequence of coefficients of the formal Taylor expansion of a holonomic function is always a holonomic sequence. And these transformations going from one to the other are completely effective, mechanical. So let's just as an example, if you take the Fibonacci sequence Fn and you form, the following power series, then that actually you can verify it's equal to this rational function, which of course obeys here it'll be a second order ODE, a holonomic ODE. Okay. Okay, so let me just retrace. So this holonomic techniques have a very rich history. Let me just retrace a little bit some of the key points of that history. So let's consider first about the simplest recurrence you can think of, which is b times un plus 1 is a times un. Now, of course, the closed form solution of this will be that un is a over b to the n times whatever u0 is, and that's a geometric progression, geometric sequence. Let's now replace the constant a and b by polynomials in n. So you got b of n times un plus 1 is a of n times un. And those recurrences define the hypergeometric sequences. And the corresponding power series are the hypergeometric functions. Okay, and they have this, if you've never seen them, of course, they have this intimidating notation, which I could explain, but let me skip that. The kind of functions you get are the exponential function, logarithmic function, many trigonometric functions, binomial Bessel functions, many classical functions. And the study of hypergeometric functions, it originated already back with Wallis in the 17th century. And there was also a lot of work by Euler, by Gauss, Kummer, Riemann, Ramanujan, and even contemporary mathematicians such as Boykers and Vadim Zudelin. And nowadays, it's a major research area in its own right. Now, hypergeometric sequences are merely first-order holonomic sequences in the sense that every term depends only on the previous term, right? So it's not like even Fibonacci is second order. And the systematic study of holonomic sequences of arbitrary order, that began much later with Poincaré in the late 19th century. And what he was really interested in was asymptotics. Asymptotically, how do these sequences grow? And many other people contributed to this since. So Oscar Perron, Coman, Salvi, Flageolet, who's depicted here. But these were all kind of structural results. The algorithmic approach to holonomic sequences, which has a very different flavor, that was really initiated by this woman, Marie-Céline Fasenmeyer. So she was a Catholic nun from Pennsylvania, and she, in addition to being a Catholic nun, she did a PhD thesis at the University of Michigan in number theory. And she developed an algorithmic method to automatically elicit the recurrence relation satisfied by specifically sums of terms of hypergeometric sequences, which include binomial coefficients. This is now known as Sister Celine's method. And then there was a lot more work in the 70s and 80s by people like Gosper, Stanley, Gesell, Lipschitz. And this was all, I would say, weaponized by Zalberger in a seminal paper in 1990 called A Holonomic Systems Approach to Special Function Identities. And that paper is actually, I think, quite a deep paper because he does not just look at the single variable, univariate version of holonomic sequences, but he also looks at multivariate holonomic systems. And he actually has to use the theory of Bernstein's theory of D modules for that. So, and this is actually very powerful. And this is what has led to the algorithms that I've described earlier. In fact, together with Wilf and Pitkovsek, Zalberger wrote the book A equals B, which is quite a well-known book in this field. And it has a foreword by Don Knuth, who says, I fell in love with these procedures as soon as I learned them because they worked for me immediately. Not only did they dispose of sums that I had wrestled with long and hard in the past, they also knocked off two new problems that I was working on at the time I first tried them. The success rate was astonishing. This book will help you reach new frontiers. So this is very high praise from one of the masters of combinatorics. And this was 30 years ago. This, ever since, of course, there's not just a book, but like I said, there are implementations in Mathematica and many other packages, I'm sure. And now this is very well understood, but there are limitations. And in particular, so for instance, we know how to decide equalities. We don't know how to decide inequalities. We don't know how to compute asymptotics. So let me give you concretely three problems that one might want to solve. So the first one is this hypergeometric inequality problem is the following problem. It's an algorithmic problem. So you're given UN and VN, so two hypergeometric sequences, and you ask, is it the case that UN is always bigger than VN? Okay, so that's a question you might ask. And you want an algorithm that answers this. Another problem, a generalization of the previous one, is the positivity problem. Now, UN is an arbitrary holonomic sequence, and you ask, is it the case that UN is always non-negative? And the reason is, of course, is that you could do UN minus VN, and then that's equivalent to UN bigger or equal to VN. And the third problem is the so-called minimality problem. I've not yet defined minimality. I will in a second, but just humor me for the time being. So UN is let again UN be a holonomic sequence. And now I ask, is it minimal? And as a special case, does UN tend to zero as n tends to infinity? So again, this is an asymptotic type question you might ask. Now, all these questions, they have a distinctly analytic flavor, as opposed to what we're doing until now, which had a real algebraic flavor. And there's an anecdote on this, which I like. So this is reported by David Mador, who is a French mathematician on algebra versus analysis. So he says, I was once dining at the IHES, it must have been in 96, and I happened to be seated right next to I.M. Gelfand. When I said I wanted to become a mathematician, he asked whether I preferred algebra or analysis, and I said algebra. And then Gelfand said, I don't understand why people want to study algebra. Because in algebra, you write A equals B. But if A is equal to B, then A and B are the same thing. So you're writing A equals A, and what's the point of that? And then Mador then writes, well, I'm not as smart as Gelfand, so I wrote my PhD in algebraic geometry anyway. So I like this anecdote. But anyway, so we're now moving into much more analytic territory. So let me just again start with an example. So consider what I call the Fibonacci recurrence equation. I mean, it's a recurrence equation I think we all know and love. Xn plus 2 is Xn plus 1 plus Xn, right? I mean, I think absolutely everyone will have seen this. Now, any sequence that satisfies this equation is a so-called solution of the recurrence. And the set of solutions will be a two-dimensional vector space. A non-zero solution, UN, is minimal. I'm defining what minimality is now, which I alluded to earlier. A non-zero solution, UN, is minimal if for any other linearly independent solution, VN, linearly independent, when you view a space of solution as a vector space, we have that UN over VN tends to zero as n tends to infinity. So it's a very, very natural, this condition makes it very obvious why you would call the sequence UN minimal, okay? And now we know that a solution to Fibonacci recurrence can be written in general as un is a times phi to the n plus b times phi bar to the n with arbitrary real numbers a and b, where phi is the golden ratio and phi bar is the Galois conjugate of the golden ratio. And from this, we can immediately guess what the minimal recurrences are, right? The minimal recurrences are going to be those where a is equal to 0 and b is non-zero because we don't allow the 0. Okay, so when a is 0, you will have, it was not hard to see, you will have minimal recurrence. So let's have a look, visually, let's see what this looks like. So here I'm plotting the vector space of solutions to the Fibonacci recurrence, where I'm identifying every such infinite sequence with the first two values. Because once I've defined the first two values, the sequence is uniquely defined. So U0 and U1. So the classical Fibonacci sequence starts with 0, 1. So I've plotted that here in red. Okay, so that's the classical Fibonacci sequence. Now here's phi bar, just to see. So it's a negative number that is of magnitude a little bit less than 1. And the vector space of minimal solution, it's not a vector space. I'm going to call it a vector space. Not a vector space just because the origin does not belong to it, okay? But I'm going to otherwise call it a vector space. The vector space of minimal solution is this blue line. And the point about the blue line is that this has slope, what we call the critical ratio. This has slope, this phi bar, this Galois conjugate to the golden ratio, okay? So anything lying there is a minimal solution. So let's see some examples. So I'm going to show you a different plot here. I'm going to plot here un against n. So n is on the horizontal axis and un is on the vertical axis. So suppose I start with u0 comma u1 to be 1 comma phi bar. So the first value is 1, the second value is phi bar, and now I'm plotting u2, u3, u4. And you can see the behavior. This is a mathematical plot, so it's not something I automatically generated. You can see that it converges to 0. Okay, does that make sense? So that's un converges to 0. Now, what if I start at 1 comma something that's a tiny bit bigger, smaller in absolute value, but let's say bigger than the golden ratio, the phi bar, which is Galois conjugate. Then what happens is initially, of course, I will mimic the previous sequence very closely, but eventually I will diverge, as we can see, to plus infinity. And if I were to start at 1 comma something that's a little bit below phi bar, then as you can expect, the behavior will be so. Okay, and now if we go back, the critical ratio, so this 1 comma phi bar literally is this point here, and you can see as long as the ratio of the first two terms is phi bar, you will be lying on the minimal solution, you will be tending to 0. Okay, this sequence of terms will tending to 0. Okay, let's look at the a priori numbers again. So this is the recurrence, the a priori recurrence. So the a priori numbers, they are, of course, a solution of this recurrence by definition. Another solution is this Bn. And this Bn here they're not all integers. In fact, the reason they're not integers is because to compute the terms, you have to divide by a polynomial. And so in general, it's going to be, Donzagier referred to it as a miracle when they're all integers. It's very rare that these numbers are integers. In general, they're going to be rational numbers. So the Bn here, they begin with 0 and 6. As opposed to 1 and 5. If you begin with 1 and 5, you get the a priori numbers, and miraculously, they're always integers. The 0, if you begin with 0, 6, you get a bunch of rational numbers, okay? And now let us take a linear combination of these two. So Bn minus zeta of 3 times An. And by linearity, this is also the solution of the a priori recurrence, of course. And the punchline of the a priori proof is the fact that un tends to 0 very fast, as n tends to infinity. And if un tends to 0 very fast, that means that zeta of 3 can be approximated very quickly by rational numbers. And now by elementary means, if you look at the a priori proof, then you conclude that it gets approximated too quickly to be rational. And therefore, zeta of 3 is irrational. Okay, that's, I'm not going to say more, but that's the punchline of the proof. From our point of view, an immediate consequence of the fact that un tends to 0 is the fact that un, you can see easily that un is a minimal solution. And so what's the critical ratio? Remember, the critical ratio was the slope of this, this blue line. So what is the critical ratio of the a priori numbers? it is, well, you can compute it from this equation here. It's going to be 5 minus 6 over zeta of 3. So here we see the critical ratio is not, on the face of it, even an algebraic number. Most people don't think zeta of 3 is algebraic. It's even a transcendental number. So it can be quite complicated, right? Okay. So now this leads us to having to compare real numbers. So here's a question. I have a purported equality here. Maybe two sides are equal, maybe not. I'm asking, are these two sides equal? Well, it turns out they're not equal, but the two sides actually agree to over 42 billion digits. Okay. And now this is a very entertaining example taken from this paper by the Borwein brothers called Strange Series and High Precision Fraud. So this is what they call the high precision fraud. Okay, you're purporting to give a series for square root pi, and it takes a lot of computational power to exhibit the fraud. But this is the point here is that comparing real numbers is in general difficult. There is a class for which we perhaps have a chance, and this is a class of periods. They were formally defined by Kontsevich and Zagier 25 years ago. So a period is a complex number whose imaginary parts are values of integrals of algebraic functions over semi-algebraic domains. So it looks like something like this. So D is a semi-algebraic domain. I won't say what this is. Just ignore it if you don't know what semi-algebraic sets are. And G is an algebraic function. Oops, sorry. G is an algebraic function. So here's the period. That's the typical period. So let's see some examples of periods. So all algebraic numbers are periods because of this. Well, you can see from this equation. Pi is a period. Here, that's the area of the semicircle, which actually is equal of the unit semicircle, so equal to pi. Log 2 is a period, of course, very easy algebraic integral. And our old friend zeta of 3 is a period. In fact, all the zeta evaluated at integers are period. But this period is interesting. This is a so-called a 3 period. It's not a 1 period because it's not a univariate integral, whereas all the other 3 integrals that are on your screen are 1 periods because they only depend on one variable, right? Just x. And so a class of 1 periods, we'll come back to it in a second. Now, the notion of period, in fact, goes back to Grothendieck. There is even this period conjecture, which I'm going to skip. But an essentially equivalent conjecture was formulated by Kontsevich and Zagier, which is essentially, it's decidable. There's an algorithm whether 2 given periods are equal or not. Even though the paper in which they write about this, there is no algorithm, but actually there is, if you look at the paper. Okay. Now, this is wide open, right? So this is the algorithmic question of deciding whether 2 periods are equal. This is wide open. However, for 1 periods, following the breakthrough work of Huber and Wisholtz, we have proven, this is together with Emre Sertoz, and who's really been the driver of this work, and James Worrell, this is currently under review, that the equality of 1 period is decidable. So in particular, if I give you a 1 period alpha, there's an algorithm that can tell you whether alpha is equal to 0 or not. Okay, so I will now tell you what this has to do with holonomic sequences. So just bear with me, it's all coming together. Let's look at an example. So consider the following. So it's a second order degree 1 recurrence. So why is it second order? First of all, it's a recurrence. Okay, so we've got xn, which is defined in terms of xn minus 1, xn minus 2. It's order 2, right? Every term depends on the previous 2 terms. And it's degree 1. The reason it's degree 1 is that all these polynomials have degree 1, which is, so they're all linear polynomials in N. Okay, now, here's a problem I want to consider for this class. So the class of second order degree 1 recurrences. I want to consider the following problem. I want to decide. So given the first 2 terms, and I apologize, instead of starting at 0 and 1 for technical reasons, and this is because of the literature, we start at minus 1, 0. So our sequences start at minus 1. Instead of starting at 0 and 1, they're started minus 1, 0. So given the first 2 values, and let's assume they're rational numbers or maybe real algebraic numbers, we want to determine whether the full sequence is minimal. Or perhaps another problem, and they're related, whether the full sequence is positive. Positive means they're always, every un is greater or equal to 0. That's an algorithmic problem. Can we do this? Okay. Now, let's see. So first I have to introduce one more technical piece of notation. So for each n, I need to consider this characteristic polynomial. So the characteristic polynomial here, it's a polynomial in Z. So n is fixed. And these coefficients here, they are directly taken from the coefficients of the recurrence. So I form this characteristic polynomial. And the root for each n, I denote little lambda n and big lambda n. And you can show that small lambda n tends to 1. So let's call it little lambda. Big lambda n tends to big lambda, which happens to be 2. And there is this very classical result, this Poincaré-Perron theorem, that tells you that for any solution sequence un, the ratio of consecutive terms will always tend to either the small root or the big root. Okay, so this is a general theorem. So either un over un minus 1 tends to little lambda, or they will tend to big lambda. And you can guess that un will be minimal if and only if un over un minus 1 tends to small lambda. Because if un over un minus 1 tends to small lambda, it means the growth is slow. Whereas if un over un minus 1 tends to big lambda, the growth is obviously large. Okay, so far so good. Last technical ingredient I need is approximating the critical ratio. So I rewrite this recurrence as follows, and I invoke another classical result, the so-called Pinker's theorem. And it tells you that the recurrence, the critical ratio is given by this infinite continued fraction. And of course, you can approximate this arbitrarily closely. And it turns out, in the case of the particular recurrent sequence that I chose, the critical ratio is this number. Now, if you ask me, is this a rational number? Is this an algebraic number? I have no idea. I can approximate to arbitrary high precision. I have no idea. If you ask me, I would say, oh, I mean, I would guess it's a transcendental number just because, but I have no idea. I mean, that's a problem. So if I want to compare, if I have, a ratio of 2 initial terms, and I need to compare it with a critical ratio, I need to know, I don't know how to do this, right? I don't know how to decide if they're equal or if one is bigger than the other. Of course, if one is bigger than the other, I can eventually numerically see this. But if they're equal, I can never know how to prove this, at least not from this formula, because there's absolutely no way I can compute a closed form for this formula. In general, this is a very difficult problem. Okay. So let me now plot, so still for the sequence we have in mind, right? This is the sequence here. Here. I'm going to, sorry, this is recurrence. I'm going to plot un over un minus 1, so the ratio of consecutive term, against n. So n is on the axis, and the ratio of consecutive terms is going to be on the vertical axis. Okay. So let me first, mu here, this critical ratio is 0.5 something, it's here. Little lambda was a little root, was 1, and big lambda, the big root was 2, it's thus. Now, if the ratio of consecutive term for n equals 0, if the ratio of consecutive term is exactly equal to the critical ratio, by definition, I am minimal. And therefore, by the Perron-Poincaré theorem, the ratio of consecutive term will converge to little lambda. And this is how it converges. This is a mathematical plot. If I start with the ratio of the first two terms a little bit above mu, then I will converge, again, by the Perron-Poincaré theorem, I will converge to big lambda. And if I'm a little bit closer, I will follow for a little bit longer, but eventually I converge to big lambda. And if I start below, what happens is interesting. I will dip to negative, and then I will overshoot to positive and converge to big lambda. Remember, the ratio of consecutive terms has to converge either to big lambda or to small lambda by the Perron-Poincaré theorem. And if I start a little bit below mu, but very close, but still not equal to mu, then it will look like this. This is a general phenomenon. Now, here's the thing. If I ask you, is the sequence always positive? Well, it's completely clear. If the ratio of consecutive terms is less than lambda, the answer is no. And if the ratio of mu, the first two consecutive terms, if it's above or equal to mu, then the answer is yes. So I find myself in the position of having to decide whether the ratio of two consecutive terms, so let's say an algebraic number, is equal to mu or not. But I don't even know if mu is an algebraic number. So how the hell, or a rational number or whatever, how the hell do I calculate this? How the hell do I decide this? The answer is I can do this, but I have to use some sneaky way. And this is how it works. I form the following generating function. So f of x is the sum of the UNs times x to the n. I have to shift by 1. And now remember, the fundamental, well, here's the thing. First of all, what is the radius of convergence of f as a function from the reals to the reals? Well, if the ratio of consecutive terms tends to 2, the radius of convergence of f will have to be a half. But if the ratio of consecutive terms tends to 1, which is really the case I'm trying to decide, then the radius of convergence will be 1, right? Because if I'm on the critical ratio, that's the only case in which the ratio of consecutive terms will tend to 1. And if the ratio of consecutive terms tend to 1 by the ratio test, the radius of convergence will be 1. So I need to decide whether f has a radius of convergence of a half or 1. And these are the only two possibilities, again by the Perron-Poincaré theorem. How do I do this? Well, f satisfies, by the fundamental theorem of Holonomic theory, satisfies the differential equation. So I've written the differential equation for you here. You can solve it using classical means. And let's look at the solution. The solution is a pole at x equals a half. So how on earth can f have a radius of convergence of 1 and not a half? Well, the only way f can have a radius of convergence of 1 is if the component in blue at the top cancels out the pole in red at the bottom. That's the only way you can have a radius of convergence 1. And otherwise, you have a radius of convergence of a half. So that means that blue part has to be equal to 0. Okay, so un is minimal if and only if that blue part's equal to 0. And if you look at the blue part, it looks a bit like, oh, what is this? It's actually an algebraic function because, well, this u0 is given to you. U minus 1 is given to you. These are algebraic numbers. So you just plug in whatever algebraic numbers you've been given, and then you have an honest to God period. Well, we're trying to decide if an honest to God period, a 1 period, is equal to 0. And I've just claimed earlier, we have an algorithm to do this. So we can decide. So just to summarize, un is minimal if that integral is equal to 0, which we can decide. And un is positive if either un is minimal or the ratio of the first two consecutive terms is strictly greater than mu. And again, you can decide that if they're greater than mu, eventually by numerical approximation, you'll be able to prove this. Okay, so just to summarize, if you consider holonomic sequences over real algebraic numbers, for second order sequences, the positivity problem actually reduces to the minimality problem. And for second order degree 1 sequences that have rational roots, here the roots were 1 and 2, the positivity in the minimality problem reduced to whether a 1 period vanishes and is decidable. And finally, you can ask, well, what if you had irrational roots? Then if you had complex conjugate roots, it would be okay because then you'd have oscillating behavior. It would never be positive. But if you had irrational roots, or for the general hypergeometric inequality problem, this can be reduced to equality of special functions, in particular hypergeometric and beta functions evaluated at real algebraic points. And then you need to decide if these things are equal to 0 or not, or rather compare these things to, you have to decide whether the special functions evaluated at real algebraic points are equal. In general, we do not know how to do this, and these do not appear to be periods or even exponential periods. So you can ask, what happens with higher degree? We're looking at linear polynomials. We don't even know if this would reduce to a vanishing integral condition. So this is completely open. So what's the outlook? Well, holonomic sequences, holonomic techniques it's a classical field of study. It's been very, very closely, the algebraic treatment has been is very well understood. But the algorithmic treatment of the analytic properties is wide open. So it's ripe for further research, or perhaps, as Don Knuth might say, for transferring some of the art into science. Okay, so thanks.
Thank you very much, Joël, for this very nice talk. So if you have a question or a remark, please just unmute yourself or write in the chat. Any questions? Maybe in the meantime, I just start with one. You just in the summary at the end, you mentioned the degree 1 property that you had in your example. So where did you actually use that property in your reasoning?
So it's a very good question. When you write the differential equation, when you have linear polynomials, the differential equation is this order two, or order one linear differential equation. Let me just perhaps I reshare
Yeah,
my
yeah.
screen again, and
Thank you.
it'll be a bit clearer. Oops, what did I do with the? Oh yeah, there's here. You can see my screen.
Yes.
Okay, so if you look at the differential equation, when the degree one means you have a linear differential equation of order one. If I had degree two, this would be a high order. I'd get some f double prime terms here. Okay, I get f prime terms because I killed the degree one essentially killed in one iteration of the
Uh-huh.
when I differentiate. If I had an f double prime term, then I don't know how to there's very nice closed form. There's a standard recipe for obtaining it mechanically from this differential equation, but we don't know how to do this for a high order holonomic differential equation or holonomic linear differential equation with polynomial coefficients. So that's the problem. And
Okay.
so I don't get a solution like this where it happens to be a period, and therefore I can use this tool that we have.
Okay,
Does that
thank
make
you.
sense?
Yeah, absolutely. Thank you very much. There is a question in the chat by Bertrand. Thanks for your talk, Joel. There came in another one, so I have to scroll. Just a
Oh,
moment.
in the chat, so I should read it.
Yeah, yeah.
Oh, yeah, yeah. Does
So
it
I'm
Poirot?
reading this from the chat.
Yeah.
Yeah. So does the Poincaré-Perron theorem apply to Rth order holonomic sequences where R is at least 3? Any bound for R?
Yes, no, correct. It does. And there's no bound for R, but of course, there can be more than one limit. So this, I think, one good source for this is either Manuel Kauer's uh, the the complete tetrahedron or something like this. So Manuel Kauer's is a book. It's got tetrahedron in the title, or Flageolet's classical book. I forget the title now, where they discuss. The Poincaré-Perron theorem in detail. Yeah, the answer is very general. So the asymptotics of holonomic sequences, as asymptotics, are well understood. If you're trying to decide whether you're always greater or equal to zero or not, and so on, this is a bit more difficult, which is, yeah.
Okay, from the chat, it seems Bertrand is satisfied with your
Yeah.
answer. Thank you. There's a second question in the chat. Jacques Solo asks, in the two first decidability theorems, what is the input just in quotation marks sequence, respectively a function, or initial conditions plus recurrence, respectively differential equation? What's the input?
Yeah, the input is you need to give the recurrence or the differential equation. So the way you specify this are you remember the polynomials all had to have rational coefficients. So you have to give all these polynomials that all have rational coefficients. It's finitary, and then you need to give the initial terms. And again, we assume these initial terms were either rational numbers or, let's say, real algebraic numbers, or for that matter, you could even have complex algebraic numbers. And these also can be described mechanically in using a finite amount of data. So you need both the recurrence and the initial values for these equality theorems.
Are there further questions or remarks?
I have a question. Yeah, so I have a memory from a talk by your collaborator, Emre Can, on computations on one morphisms. When I was in Oxford, Ben invited me for that talk. So I think your algorithm was based on a theorem by, I guess, Uber and someone else, which says that one periods are morphisms of certain one motifs, and those one motifs have certain forms. And I guess they were like from some free modules to some abelian varieties or semi-abelian varieties. Can you say how you construct those one motifs? Because I'm really wondering how you construct
Um,
abelian varieties. And then
so
your algorithm, if I remember correctly, based on the construction, you computed Turan cohomology, Petit homology
Yeah.
comparisons and so on. Can you
It's
comment?
very involved. The short answer is I can't really describe this in a sort of nutshell. The paper is on my website if anybody wants to look at it. I mean, it's under review, but you can find it under publications. It's got transcendence, something, and one periods. The we are actually we have Emre and I are co-supervising two PhD students who are currently one of the tasks that we've set them is to actually implement this. So hopefully, within within a few months, we will have a tool, an online tool, where you will be able to put in, let's say, log 3 and then some other one period, and ask, are these equal, or are these, for that matter, linearly? What are the multiplicative relations that that hold amongst them? So all these things will be automatically elicited by the algorithm. But I cannot, yeah, this is quite involved. So I cannot answer, I can't answer in a nutshell, I can't answer here. And also, I would have to say, Emre would be much better placed than me to answer this kind of question.
Yeah, just out of curiosity, maybe something more general. So you represented one period as integral of something, and there was a curve
Yeah,
constructed there.
yeah.
Is this the case, or this is the
Well,
question?
not in this talk. So what happens in this talk is you just have an integral. Now, underlying this integral is just an integral over the reals, right? You integrate from, it was from 0 to 1, and you have this algebraic function. Now, when you do this work with one periods, of course, you move to a different space, and then you have to look at the curve that you have. You have to look at its genus. You have to start doing all kinds of, complicated calculations that will depend very much on the algebraic function under consideration. And then, so the algorithm will construct many different objects, cohomological objects, in order to finally come up with the answer. Is this equal to 0 or not? But this is sort of completely absent from the talk that I just gave. You simply solve the differential equation, and that's an integral. And in general, you can show that these integrals of this kind will always be one periods.
Okay, are there further questions or remarks?
Yeah, so if I can just quickly address the question asked. So the bread and butter of the algorithm is to visualize all these. You mentioned relative relations between one motives. So all of these are realized in terms of correspondences in the Jacobian of the input curve. So you can move to something called the Jacobian, and it has a bunch of endomorphisms, which it's a finitely generated algebra. And a subroutine in the algorithm is to compute this endomorphism algebra. And once you do that, you can essentially list all the possible relations. So yeah, that's essentially how it works.
Thanks, thanks, Madhavan. I owe you one.
Further questions or remarks? Just checking the chat. As far as I can see or hear, this doesn't seem to be the case. So we thank Joël again for this great talk. Thank you very much. And
Well, yeah, thanks very much, everyone. So have a nice weekend.
Yeah, have a nice weekend, everyone. And we resume next week. See you then.